I just realized we have no clicker. Thank you. I thought we might need this. All right, welcome everyone. Welcome to Games First and our first talk, Giving Artists Superpowers. First of all, let's give some introductions. My name is Stoyan Dimirov. I'm a technical artist at Space Ape Games. I've been there for 5 years now, and before that I used to be a character artist in the console industry. I guess one day I got tired of it and went into technical art. And this is Michael.
Yeah, I'm Michael Short. I've been in the games industry for about 10 years now. I spent most of that as a AAA console developer, rendering engineer. I moved to Space Ape about 2.5 years ago as a client dev.
All right. So to give you a bit of a story about Space Ape and what was our journey in terms of art and tech, the first game that we made was called Samurai Siege. It was a build and battle game. And it was mostly made out of these pre-rendered 2D characters. So they look 3D, but they're all in 2D. It's all an illusion. You can see the animation is quite choppy. And with the next game, we wanted to push it a little bit further. It was called Rival Kingdoms. And the characters in real-time 3D. And the animations are much, much smoother now, running at 30 frames per second. But in terms of shading, it was very basic. It was just a flat texture applied on the model. You cannot change the lighting. It's all baked down. It's all the same all the time. The next game, though, Transformers Earth Wars, we wanted to make the characters our main focus. There was 100+ Transformers in the game. So we wanted them to look shiny. We wanted to have big close-ups of them. They were not small on the screen anymore. So we started using things like PBR shaders, normal maps, specular maps. So all of your buzzwords for like next-gen stuff. And at that point, we ran an art team survey. So we run an art team survey with, the art team every quarter. And we just kind of do it to gauge how they feel about making games, the process, working as a team together. And something that came out of that survey that time, after Transformers, was this. We want to be the best on mobile, but we're really behind on tech. And for us, that was a bit of a wake-up call. We're like, we need to sit down and do something. Space Ape changed, so we took a different approach how we make games after Transformers. Transformers was made by 30 people, and after that we thought maybe we need to work in smaller teams. We need to validate ideas a lot quicker than I think Transformers took about 18 months to make. We want to validate ideas a lot quicker, see if they're good, so we split the studio in much smaller teams. Some of them were about 3 to 4 people, so really, really small. Of course, those people still wanted good graphics. They still wanted to produce a lot of content very quickly, but there was nobody to kind of just sit down and make tools or make shaders for those games. So it was a problem. We saw there was a bit of a gap for some other team to help them out. And this is where we came in, the tech art team. There's 3 of us. There's me, Michael, and Nick Williams. I'm hoping he's somewhere in the crowd today. We called ourselves Art Labs back then, and that's why we have this beaker as a logo. And all the games were named after animals. That's why we have the animal icons. So before we got to work, we were very excited. It wasn't hard to find people for that team. Everybody wanted to do shaders and tools. It was very, very exciting for us. But we thought before we start working, we need to figure out what the hell are we going to do. So we came out with these pillars. So these pillars were meant to focus our work a little bit. The first of all was visual quality. We wanted to make games that are the best on mobile. And that doesn't mean only your kind of console level shaders and techniques, but also giving artists freedom to produce any kind of art style they want. And of course, making good shaders and good graphics doesn't mean it's quick. We wanted artists to be able to make that content very, very quick. So our next pillar was art efficiency, where we started making some tools to help people make content faster. And both of these are founded on performance, because performance for us is very, very important. We take it very seriously. We want everything that we make and produce for artists to be smooth, efficient, and cool. Cool as your phone used to be cool after we're done with it. We're not making pocket heaters, even though in this weather it might be quite nice. So we got to work, and for the past year we made a few, quite a few cool things that we wanted to show you, put them together in a reel. And keep in mind, everything is designed and engineered for mobile. So yeah, please enjoy.
I'm gonna take it all the way when I hear the music play, 'cause baby I can't help myself. I'm here to do my tomorrow brings. I'm never gonna kiss and tell. I just wanna have fun. Show me what you got, 'cause the floor is getting hot. I wanna see the way you move. It's time to get it on, gonna party all night long. This is what we do. La 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 la, I'm all about. Come get it, come get it. La 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 la, I'm all about fun. Get it, come get it. I wanna dance the night away until we see the light of day. Come give me some. We're never gonna stop, 'cause we never get enough. We burn till we're out of time. And when we get to the end, we're gonna do it again. 'Cause tonight is when we come alive. I just wanna have fun. La 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 la, I'm all about it. Come get it, come get it. Oh yeah, come get it, come get it. I wanna dance the night away until we see the light of day. Come give me some.
Thank you. So obviously there was a lot of stuff in there. We can't show you or talk about everything today. So instead, me and Michael are going to dive into two kind of things we're focusing on for the past year. First of which is our rendering. And give it up for Michael.
Yeah, so I'm going to be talking about physically based shading and how we brought that to mobile over the last few months. For like a bit of background, all of our art team use a package called Substance Painter. It's like a 3D real-time like software package, and you can paint on models in 3D in real time, and it will show you the effects of it. And then at the end of it, you export this texture, and you bring that into Unity. And about 2 years ago now, I guess, like Unity released this standard shader, and this is kind of like the replacement for the old school mobile diffuse shaders. And this is like a PBR-based shader, and it looks like really, really close to the substance material, but it's not quite like where we want to be. It's a bit like the colors are a bit more washed out, and the reflections aren't quite the same. And then our art team end up like having to go in and reconfigure textures and like change material parameters, and it's quite frustrating for them. And like this material was originally developed for console and PC as well, so like although it does run on mobile, it doesn't like run as well as we want it to. So like we went away and like thought about how we're gonna sort this out. And our first attempt, we created this thing we now know as a Uber shader. So we created these goals to help drive this project forward. And the first one was it had to be flexible. Like Stoyan says, we have like a lot of game teams, and they all have different requirements and like different features, and all the games look different. So it needs to be really flexible for them. We need to let our artists debug the shader, so if there's a problem, they can easily get down to the issue of it. We need to have different light models, so all of our game teams have the option to change light models whenever they want. We want to transition from gamma to linear color space. This one shader should be like cover 95% of all cases. It should be the one shader to rule them all, and it means our game teams don't have to spend a lot of time creating shaders. And finally, we're a mobile-only studio, so it needs to be really performant, and it needs to run really well. So when we look at the first thing, flexibility, like I said, each of our game teams has like a different set of requirements. Like all the artists work in different ways, and they blend textures in different ways. And on top of that as well, we have lots of global effects. We have like the color correction, motion blur, and things like that, which you saw in the reel. And we tie some of that into our shader, and we mask areas out in using the alpha channel and stuff. And we can't just inject that into the standard shader because it's a bit of a closed box. So Stoyan did a really good talk on this, and it's available online. There's a link there. We basically used Unity's shader feature system, and created this really, really flexible shader for our artists to use. And there's hundreds of options you can enable and disable everything. I can say, because Stoyan's already talked about it, I'd recommend you go and look at that, hit that link up and look at it. It's a really, really good talk. And after that, I mentioned we have to let our artists debug any issues. So if there's a problem, we don't have to run the game on device and then do a frame capture in Xcode and then try and figure out what's going on. So what we did is we exposed all these different views. So all the different inputs that go into the material, we let the artist toggle them on and off, and then this works in editor and on device as well, so they can quickly like get down to like what the problem is. Like say if one of the normal maps is broken, they can go in and quickly track down that issue. And as this is a debug feature, we just like hard coded it. It's like a massive if statement. It doesn't run very well, but like this is like say a debug feature, so it's not going to make it into the final game. It's just to help our art team discover issues really quickly. So with lighting models, like I said, like we wanted to like allow our game teams to use like loads of different lighting models. Some of them want to use the bling fong model. Some of them want to use like a new GGX specular model. But we don't want to have to make all the game teams write all these like complex lighting equations. So what we ended up doing is baking these light values into a lookup texture, and then like the artist can quickly swap in and out different textures at runtime. And then like, it's just like a simple texture lookup, and it's really quick, and it means like the artist can like select whatever light model they want, and we provide loads of these out of the box, and they can create their own if they want to. And we also wanted to like transition away from gamma space lighting to linear space. Like the console industry's done this over like the last 10 years now. And for those that aren't aware, like textures and colors are in something that's called gamma space, and all your shader maths is in another space which is known as linear space. And when you try and multiply these values together or add them together, these values are in different like color spaces, so it doesn't make any sense. So the idea behind this is you convert all your gamma space values to linear space, do all your shader maths, and then at the end convert it back to gamma space for your render target. And a lot of people actually look at those two spheres there and they'll think like, well, the gamma space one looks more realistic. But I took a picture of this Lego dude on my desk, and if you look at like the transition between the lit and the unlit area, you can see it's like quite tight, and it's like much more accurate when you look at the linear version of the sphere. So we want to give that option to our art team. And we did this as like a project-wide setting. They can fire up this window, like select gamma space, linear space, hit apply, and then like that's it for your game project. And it's as we did this via like a shader feature again, it can be disabled on lower end platforms. And this means like if like you've got a regular device that's running slow, you can save a few GPU cycles. And we use an approximation. We use like the square root and the square of the color value, which is like kind of like 95% accurate, and it gets us like really close to what we want it to do, and it's not as expensive as like the true way of doing it. And then you can copy and paste that code if you want. So the final one was performance. Unfortunately, we actually like regressed a little bit. We were about 11% slower than the standard shader. And when we looked into this is because we were making more texture reads. And that's because we like moved all of our lighting values into this like light lookup texture. And on top of that, if we wanted more lights in the scene, like say we have 10 lights, we have to like read that texture 10 times, so it doesn't scale all that well. So we tended to stick to like one light for each of our scenes in Unity. So if we go back to our problems, like we can see we've solved like color space, flexibility, and debugging, but we've made like a regression with performance. And then on top of that, we've identified that we've not quite got there with visual parity yet, and we've like introduced this balancing issue, which I'm going to go into in a second. So when we talk about visual parity, like we can see here, we've got like Substance Painter, and then we've got like the same guy on a mobile device, and it looks like a lot closer to Substance than the standard shader does. But when you actually zoom in, and like our teams like always zoom in on these type of things, you can see like when you look at like the leather glove, you've lost a bit of specular lighting off there. The light's a bit different on the arm, and then like the metal isn't quite the same. And again, it's just frustrating for our art team. They have to go in and make all these tweaks. It takes time. And like with balancing, because we made this thing so flexible, the interface became quite complicated for the art team. And it became really hard to balance things because you can enable and disable any feature of the shader. And this kind of meant like every surface in the game with like a different feature set is going through a completely different lighting model. So like everything ended up looking different. So we wanted to like take what we'd done right and then like try and fix what we'd done wrong. So we went back to the drawing board and came up with like a new project. And this is like now known as the PBR shader. So for those who don't know, PBR stands for like physically based rendering. It's also known as like physically based shading. And it's essentially just a framework. Your light values and your material values are like physically based properties. But more importantly, like all the textures and inputs that your art team have, they're all like, you have guidelines for them, and it's like a lot less guesswork because they have like a frame of reference. And the other side of this is like to do with energy conservation. You can roughly break light down into two different categories. You've got like diffuse light and reflectance. And like if you have more diffuse, you have less reflectance, and like the other way around as well. So you've got to balance these two like light sources out. And like a surface can't reflect more light than you give it. It doesn't make any sense. And then like in more simple terms, like it's like this one shader can kind of like render all these different types of surfaces. So it's like really useful and it's really quick and easy to understand because it's all got the same interface. So I mentioned we baked all of our lights into this lookup texture, our lighting values into lookup texture, but our game teams just ended up using the GGX model. And for those who don't know, the GGX model, it's just like another light model, a way of like representing specular highlights. It was like created in 2017, and it's like a replacement for the bling foam model, which has been around for about 30 years now. And the reason it's been around for 30 years is because it's like really cheap and it looks quite realistic. So I've got like a comparison here. There's like a real-life material scan here. So this is like a picture, I think it's of a chrome surface. And you can see you've got like a nice like intense patch in the middle, which is a specular highlight, and like a nice fall-off as well. And then when you look at the bling foam model, you've got like the really intense patch in the middle, but you lose all of that fall-off. And with the GGX model, you have like the intense area in the middle, and you also have the nice fall-off as well. It's not exactly the same, but this is like a simulation, and it's a lot nicer than the bling foam model, but it costs a lot more as well. And people tend to just use this on console because it's like more expensive. So we went away and we found this paper from SIGGRAPH 2015. It was actually by like one of the devs from Unity, and it came up with this really, really good approximation. And it's like very, very accurate and very, very similar to like the real life GGX model. So we took that, and because it's like there's a lot of source code and stuff in there that we took this equation like and put it into source code. All that source code's available like via this link, and I've included all like the research papers in there as well. So if you look that up, you can kind of like copy and paste that code in your project and get it working. And with balancing, like we kind of took all of these different options away from the artists and made it much more simple. So like, for anyone that knows like PBR, the whole idea behind it is you keep things as simple as possible for your artists. And you have this like smoothness value, which is like a 0 to 1, 0 being rough, 1 smooth, and like you can obviously have something in between. So like wood is quite rough, plastic's quite smooth. And on the other hand, you have like metallic value as well, which is like a 0 or a 1. It's either metallic or it's not. So like aluminium is metallic, whereas plastic isn't. And that's kind of it. You can define like virtually any surface with that, along with like a color map and normal maps and stuff like that as well. So it's like a really nice interface and it's really simple to use. So with visual parity, we say this is how our side-by-side comparison looks. And when you zoom in, we managed to get like it much, much closer. It's never going to be 100% like the same because like we're comparing an offline desktop renderer to a mobile device. But you can see like the specular highlight on the gloves much more accurate. The fresnel around the gloves like much more accurate as well. And then the light and then the metallic on the watch is like really close too. So our art team are really happy with this because it means they don't have to go in and reconfigure everything. So performance, if you remember like last time, we used the standard shader as like a benchmark and we actually regressed a little bit. So we need to get back down to where we were before. And we actually managed to beat it a bit as well. So we've saved quite a bit of time off when we did this. And one of the reasons for this was we used a lot more half instructions and float instructions. So this is kind of like a breakdown of like the two other shaders, like the top being like the number of float instructions in your shader, and the bottom being the number of half instructions. And you can see like with the Uber shader, we've kind of got like for every 1 float instructions, you've got 2 half instructions. And with the PBR shader, we took this to like 10 to 1. And for those that don't know, like half instructions kind of run at like twice the rate of float instructions. So like wherever you can, you should use them as much as possible. I'm going to go into a bit more detail later on. So with the raw performance stats, we can see like in virtually every category we've managed to like beat the other 2 shaders. The only one we haven't beat is like the ALU shader time, but this is because we've moved the lighting calculation from a lookup texture into ALU, which is what we want to do anyway. And we actually ended up being about 15% faster than the Unity standard shader, and are like looking more close, like much more accurate compared to it as well. So like with performance, I mentioned like we used a lot more halves and floats. Like I said, these are like twice as fast. You can get some precision issues, and you've got to watch out for these. But like it's just something to work around. It's definitely worth using these wherever possible. When you are using halves and floats, like stick to whichever one you choose. Don't convert between the two because it's like quite expensive, and then like the GPU doesn't like it. On top of that as well, prefetch as much texture data as you can. We had this issue, one of our shaders. This is like a breakdown of like an early breakdown of the PBR shader, and you can see like in the middle we've got this like one line of shader code that's taken almost 38% of the entire shader. And when you look at this, if you look at the line above, that's like reading a texture, and then the line below is using that value. And what's happening is the GPU is having to fetch that texture data from main memory, and then that's like a slow process. So like the GPU is waiting for that texture data to be fetched up, and it's like stalling the GPU. So essentially the GPU is sitting there doing nothing, just waiting for that memory to be available. So to get around this, all we did is we moved that texture to the very beginning of our shader, and then by the time we need that data, it's ready to use. And that stall went from 38% to 4%. So that's like a really easy win. On top of that, we found like we were passing way too much data between the vertex and pixel shader. So we've got this again, this is a breakdown of an early breakdown of the shader, and you can see here under the ALU cost is this other category. Ooh. There's this other category. Can you still hear me? Cool. This other category, we had to go back to Apple and ask them what was going on, and they essentially said this is interpolation cost. So 50% of our shader time was spent just interpolating, blending values between the vertex and pixel shader. And the only way around this is to pass less data between the two, or use halves instead of floats again. We managed to get this down to about 33%. It's still more than we'd like, but it's better than 50%. Use as fewer texture fetches as possible. Mobile devices have really small buses, so they have not much bandwidth at all. So just try and use as fewer textures as possible, and where you do use textures, make sure they're compressed and use bitmaps as well. And finally, this is to do with linear space lighting. We have to support OpenGL ES2, and that doesn't support sRGB texture samplers. And what this is the GPU has a hardware unit, and when you read a texture, it will convert from linear space, from gamma space to linear space for you. And this is much faster when the GPU does it for you. We found it was about 8% faster than doing it in our shaders. But because we need to support OpenGL ES2, we have to do it the other way. But if you don't, use sRGB samplers. So I think next up we've got a video of the PBR shader working on device, and then I'm going to get Stoyan back on stage to talk about one of the tools he's been developing.
Cool, so now that we've seen how we shape things, it's time to see how we model them. So I'm going to talk about a Houdini track generator that we made last year. Before I get into it, I want to give you a little bit of context where it came from. A few years ago, we started making this kart racing game on mobile, and very early on, we knew that we're going to need tons and tons of tracks. We want to iterate very quickly on them. They're going to have varying width, very kind of small variations in curvature. They're going to have different levels. So we knew that we're going to need some good tooling for that. There are a few ways that you can make tracks out there. I've seen people use these kind of pre-made track parts. So they make it in a 3D software and then just stick them together, very, very similar to those electric toy tracks you have. There is another way where you get those parts and you deform them along a curve. And this is the way we went for because it gave us a lot of freedom. It means we can have a lot of variation in terms of curvature. We have a lot of control in every step of the way. And the way we did it was we made these segments of the track in 3D software. So this was made in Maya in this case. And we subdivided that segment, and then we deformed it along the curve. And that's how you get the track. Very, very simple. And this is the editor in action. So you have these points that you adjust by hand, and you get a preview, an outline of the track. You can control different parameters on the track itself. So you can control the width of the road. You can control how wide the off-road is on both on the left and the right side. And again, this is done per point because we needed that control along the track itself. Everything updates in real time in terms of the outline, but there was a disadvantage where you don't really see the final result of the track. We also had a curb as well that you put in by hand. And every segment that you saw earlier, you need to specify for each and every point. So there's a lot of user input, but you don't see the final result in real time. But the biggest drawback was that after you do this, you click a button, and then you wait 4.5 minutes for your track to bake and for you to see it. That is enough time to go and grab a coffee And you think, okay, this is not that much time. But if you multiply by 20 times, which is about how much you're going to edit a track per day, that's an hour and a half just staring at a progress bar. That's a lot of caffeine as well if you go for coffee every time. So this is what we end up with. The algorithm has done its job. It deformed all the meshes. But there were some issues. If you look closer, the walls were quite jaggy. They were not deforming along the track very well. There was some squishing of the mesh, squishing of textures. There was stretching along the turns, the corners. And also those caps on the walls, they also get squished. So small details were not handled very well by that kind of curve deformation algorithm. So we had to fix that. There was another issue as well, performance. This track was 73,000 verts. Our budget was only 30,000. We wanted to target 60 FPS on both high and low-end devices. And this was just not cutting it. There was quite a lot of verts. And that means, so vertices are the points that make up the track, that make up the mesh. The more you have, the less it's going to perform. And the bigger it is on disk. So we had, I don't know, 20 to 30 tracks, and that is a lot of file size. So it was very big. We need to do something. First thing we could have done is get those segments. So if it's a straight segment of a track, we can totally kill these things in the middle. And you can remove them very safely. You only need these divisions for the bendy parts of the track. You don't need them from the straight parts. And the other thing was these caps for the wall. So they look nice visually, but there's also quite a lot of them in the track, so we couldn't allow for too many of them. They were very point dense, a lot of vertices, so we had to remove them and make one continuous wall. Unfortunately, that wasn't doable just by deforming an existing mesh along a spline. We needed a different approach. So this is where Houdini came in. And Houdini is a lot of things for a lot of different people. For us, it was more of a procedural mesh generator. And lucky for us, the Houdini engine is actually very easy to integrate in Unity. Unity is the engine we use. You just install a package and it just runs. You can make tools in Houdini that run real-time in Unity. So I'll show you how the road creator actually works. Just a brief snapshot. Notice how the nodes on the right update for the viewport on the left. So first of all, we take points, those points we drag into the Unity viewport. We interpolate them, so we add some more points between those points to create a smooth curve. And then we use Houdini's refine node, which does exactly what it says. It just kills those points on the straight lines and keeps them on the curvature of the track. So we get this line that we duplicate along those points, and you get this extrusion of road. This is the final result. And notice how the texture changes based on the curvature of the track. This is very important. This is something we use later on for different parts. But in this case, we just use it to update the texture. For the markings of the track, we used a similar technique. We just took those points in the middle, we extruded them outwards, and then you get your markings. You combine them with the road, and that's the final thing. So to see it in action in the editor, you can see Houdini engine is running in the editor in real time. You can just tweak things very, very quickly. And because the whole mesh is procedural, you can adjust anything you want, from the width of the markings, their position, anything. The best part is it updates instantly. So there's no time for breaks now. There's no time for coffee. The artists were so happy. And notice how the meshes are updating. So they're updating towards the curvature of the track. So the more straight the track is, the less segments you have. So that was very useful for performance for us. Of course, we have the previous parameters that we had. So we can update the road width, but now you see the actual road updating in real time. You have your off-road, which is done the exact same way as the road. It's just another line duplicated another line. It's just, that's how it is. And it's all updating in real time. You can see the textures are updating, the UVs are updating, everything is right in front of you. So far so good. We had a road, but we don't have walls. So how do we do the walls? How do we get over that barrier? Sorry, that's the last one. So we made these end caps. So these are done by a 3D artist. And we take the profile of the end cap, and very, very similar to the road, we just take that and we extrude it along the line. And we have the profile of the wall. And then we just take the end cap, duplicate it twice on each side, slap some textures on, and that's your wall. This system is simple, but it gives you a lot of freedom because everything is procedural again. Just by changing the end cap, changing the textures gives you quite a lot of variation in terms of wall. And we did need that variation just to have different walls depending on the curvature of the track. So this is the tool in action again with the walls. We put the walls on, and they update in real time as well. They conform absolutely perfectly towards the track because they're designed for it. They're made from scratch every single time you update a track. Notice how if we increase the curvature, the walls change, so the mesh changes. The texture is also changed. This is done automatically by Houdini. And for the sharper turns, we had a different type of wall. We also had an apex that was generated automatically as well. You can adjust the width of that if you wanted to. And yeah, that just gave you a lot of flexibility and very, very kind of quick turnaround, quick feedback while you're working. We also wanted to remove walls so carts can fall off of it, and we also wanted to remove the whole track in some cases. And notice how there's end caps. These get added exactly the same way as the walls. So we use the same technique, very, very simple technique all over the track, but it gave us a lot of variation very quickly. And yeah, that's the tool in action. So after we did all this, this is the final result. Very, very similar to what we had before. And with some lighting and some props, this is the actual final version of the track itself. But what about performance? So we had 73,000 verts before. And after Houdini's magic, removing all those verts, we have 13,000 verts. That was great. That was half our budget, less than half. So now we could hit our 60 FPS, and it was very, very kind of small footprint on device as well. So I just want to show you now how it looked in the actual race. So yeah, please enjoy. Thank you.
So we are now going to have a Q&A. If you want to just stick up your hand if you have a question, we've got these fun catch-up boxes that will be thrown to you or handed, depending on if you're brave or not. So yeah, if you have a question, just stick up your hand real high so our team can come around. See one over there. Yes.
Hello. Well, that's new for me. So I just wanted to know how, I don't know, is there a tech team in the company? Is a tech artist assigned to a team? Is the Workflow Leather kind of like shared tech for the whole company? Like how many tech artists are there? That kind of.
So the tech art team, usually we're kind of a shared resource. So we help every game team that we can that wants our help or wants some kind of tools or tech developed for them. But there's three of us. One member actually goes into the game teams and works with them. So like the feedback loop is much, much shorter. But yeah, we tend to be centralized, and we'd like to make as many shared tools as possible so all of the games teams could use them. And yeah, I hope that answers the question.
When you're showing smoothness and metallic sliders, why you use slider for metallic and not just Boolean, if it's true or false statement?
It's just in case the artists want to do some like really weird effect, or if they want to blend between the two. I mean, in 99% of the cases, like that should never happen.
Yeah, one case is metal covered by dust. That is kind of, sort of, kind of metal, but not quite there.
Question for Michael. I didn't catch which tools you used to track how long things took in the shaders themselves.
Okay, so we use Xcode on iOS.
So you're running on device and,
Yeah.
Okay, cool.
Yeah, like we have like a number of different Android profiling tools to use as well. But we tend to find that the Xcode's quicker to use because I've got a MacBook. Yeah.
Okay, great. Thank you.
Hi. So one thing I was curious about is how long did it take you guys to do each of these? Because one of the reasons that we tend to deprioritize tool development and this kind of thing is because we're afraid of the amount of time it'll take us, the amount of time we'll quote unquote waste in the process. Like, how long did these things take you to develop?
Right. Like before I answer that, the way we think about tools is, if you think about how long it's going to take for you to make it, if that time is longer than actually making 20 tracks, for example, then it's probably not worth making a tool. For us, it took about, I don't know, for the track tools, 2 months to make. There was a lot of iteration after that, but I believe it saved a lot more than that in the end.
I think the PBR shader was like a month or two as well. We spent a lot of time researching it beforehand. But like this is getting rolled out to all of our game teams, and like yeah.
Yeah, it's also not only about time; it's about quality as well. If we didn't go for the PBR shader or track generator and we stuck to what we had before, I don't think the quality of the game would have been that high.